Hello and welcome to helpyourmath.com. In this video, we're going to look at solving Ickier exponential equations using the method of your choice. Now, when I talk about these methods, there are previous videos where I go into more detail about these, so I assume you already know or have some familiarity with these methods. The other thing you're definitely going to want with this video is a calculator. More than just a four-function calculator, you want a scientific calculator. Okay, let's review the methods first. So we have three methods that we may use to solve exponential equations. The first one is the one-to-one property, and that just says that if you can write the two sides of the equation to have the same base, then if they have the same base and it's an equation, then the exponents must also equal each other. So you could just look at just the exponents and say, well, I know that they have to equal each other, and then solve from there. Alternatively, we might use the change of base. Now I know I said exponential equations and then there's no exponents to be found here, but you could take that exponential equation and write it as a logarithm and then apply the change of base formula if you would like to use that. Now, why would we use the change of base formula? Well, because this a could be representing any positive number, right? It could be 1, probably not 1. It could be 7, it could be 8, it could be a half. We don't have a key for that on our calculator. What we do have a key for are two very specific bases. We have log base 10, which you should see on your calculator is just log. So on your calculator, if it just has log, that's log base 10. So you could have log base 10 of b over log base 10 of a, or log of b over log of a. Or you can use the natural base, which should also be a key on your calculator. You could do ln of b over ln of a, the natural log of b over the natural log of a. Either of those will work, and those are both available on your calculator, and it doesn't matter which one. They're all equal to each other, as long as you're consistent, right? If you do log of b, you have to do log of a, and you want to make sure that you're doing two separate things. So on my calculator, what happens is I type in log, and then it opens up a parenthesis. So then I would type in whatever my number is. I need to close my parenthesis before I say divided by. If I don't close that parenthesis, then what it's going to do is it's going to take log of b divided by log of a, and that's not the same thing, right? That's a very different thing. So you need to make sure on your calculator that you close the parenthesis so that it knows where the end of the argument is for that first log. So this is bad. We don't want this. We want this. Okay, so that's our change of base, and then we have taking the log of both sides. So if we have our variable stuck in the exponent, you could take the log of both sides, because what that would do is that would move the exponent to the coefficient of the side, and then you'd be able to hopefully solve from there. Again, I would be very careful about what log you're choosing. I would use either log base 10 or the natural log. And are there any restrictions on the values of x? When I'm talking about the values of x, if we're talking about an exponential equation, the variable is typically in the exponent, and no, there are no restrictions. So none of these would have any restrictions. Let's look at some examples. In our first example, we want to solve using whatever method we find most appropriate, and then we're going to round our answer, if needed, to the nearest hundredth. Before I choose any method, we want to try, if we can, to get the term with the exponent by itself. So I need to subtract 6 first and foremost before I do anything else. Okay, so now what we're looking at is 3 to the 2x plus 1 is equal to 81. I have three methods to choose from. In this case, I can choose any of them. I can get 3 and 81 to have the same base because they're both powers of 3. 3 is 3 to the first, and 81 is 3 to the fourth. So I don't even need to rewrite this side. I can just leave it as 3 to the 2x plus 1, and then I rewrite 81 as 3 to the fourth. Now I can use the one-to-one property. I have the same base, right? 3 is equal to 3. That also means that the exponents must be equal. 2x plus 1 must equal 4. I subtract 1 from both sides. 2x equals 3. Divide both sides by 2. And I end up with x equals 3 over 2. So that's using the one-to-one. I could use, if I didn't think of that, if I forgot that 81 was a power of 3, or, sometimes you just kind of fall into habits because the one-to-one property is particular, whereas the other strategies aren't. So if we got here, and then you were like, what could I do from here? You could also apply you could do the change of base, or what I'm going to do is I'm going to do the third strategy, which is take the log of both sides. And again, I can choose to do ln or log base 10. We'll do ln just for fun. So if I do ln, I would have ln of 3 to the 2x plus 1 is equal to ln of 81. And now what I'm going to do, because now I have this as my argument, I can take the exponent and put it out in front. So that'd be 2x plus 1. I need to put it inside parentheses because that whole thing is getting multiplied here. Times ln of 3 equals ln of 81. Now what I can do is I can divide both sides by ln of 3. Divide by ln of 3. So those are going to cancel here. And I know it looks scary, but ln of 3, remember, that's just a number. And if you've seen my videos before, you know that I tend to be a very precise person. So you could put that in your calculator and get an approximation for ln of 3, but I like to wait until the last possible second before I do any calculations in my calculator. Okay, and so now I have 2x plus 1, and if I do ln of 81 divided by ln of 3, I should end up with 4. So that would give me 4, whether I use a calculator or not, because again, 81 is the 4th power of 3, and that's basically what that's saying. So then I would have 2x plus 1 is equal to 4, and look, that's what we have right here. So you can see we would end up at the exact same spot as when we did the one-to-one property. So for this one, you could use any of the methods and they should all give you the same result. I mean, hopefully they do. How about this one? So here we have 5 to the 4x minus 1 equals 1 over 125 to the x minus 1. Okay, this one's tricky because we have variables on both sides in the exponents. So I'm hoping that 5 and 1 over 125 have some common, common powers to some basic base. So let's see. So 5 is the first power of 5. And what about 1 over 125? Well, 125 is 5 cubed. How do I get 5 cubed out of the denominator? I would take the exponent and make it negative. So it is possible, so these are equal. It is possible that we can use the one-to-one property again. That would be 5, I don't even need to change the 5, that's 5 to the 4x minus 1 equals 5 to the negative 3 to the x minus 1. Now here on this side, I have power to a power, so remember what we do is we multiply the powers. This does require using the distributive property because basically what it's saying is it's 5 to the negative 3 times x minus 1. So this side stays the same. Over here we would end up with negative 3x plus 3. Now that I have the same base, I can look at just the exponents. 4x minus 1 equals negative 3x plus 3. And then I'm going to add 3x to both sides, and I'm going to add 1 to both sides. Add 3x to both sides, add 1 to both sides. I end up with 7x is equal to 4. Divide both sides by 7, and we get x is equal to 4 over 7. So not so bad. And we could, of course, check our work because you could just plug these in the calculator since we have calculators. So far, we haven't needed it. These turn out pretty nice. All right, 2 more examples. As always, I suggest pause the video and see what you come up with. Okay, for the one on the left, yikes, we need to get this by itself. So I'm going to first subtract 13 from both sides. That's going to give me 8 times 4 to the 6 minus 2x is equal to 41 minus 13 is 28. Now I need to divide both sides by 8. And we end up with 4 to the 6 minus 2x is equal to, 8 doesn't go evenly into 28, but we can simplify it. They're both divisible by 4, so we could rewrite it as 7 over 2. All right, so that's pretty icky, isn't it? What can we do? Well, I'm probably not going to be able to write 4 and 7/2 as the same base, so the one-to-one property is out. I haven't yet used the change of base property. In order to use the change of base property, I would take this exponential equation and write it as a logarithmic equation. So what I would do is I would say log, and what's my base? My base is 4 of, and this would be my answer, is equal to 6 minus 2x. Now from here, this is where I want to apply the change of base because this is not something I can calculate on my calculator or in my head. So what we would do is we would rewrite this. I used ln last time, so I'll use log this time. Log of the argument divided by log of the base is equal to 6 minus 2x. Now we could plug this in our calculator to get some approximation if we want to do that now, or we can get x by itself first. Now is probably a good enough time to do this. So if we do this in our calculator where we do log of 7 over 2 or ln of 7 over 2 divided by log of 4 or ln of 4, I end up, I'm running out of space here, I end up with 0.904. I have 367, but the 6 will bump the 3 up, is equal to 6 minus 2x. Now I want to subtract 6 from both sides, and that would give me negative 5.096 is equal to negative 2x. Divide both sides by negative 2. Negative divided by negative in either case is going to be positive. And when I do 5.096 divided by 2, I get 2.548. So we get x is approximately 2.548. So that one I chose to use the change of base. It's a lot of work, and it looks a little scary, but really it's not that bad, right? It's not that bad. All right, our last example, we have 9 to the negative 5 minus 2x is equal to 431. Which one should we use? Well, the one-to-one property is out because 431 is, I don't even know what that is, but it's certainly not a power of 9 or 3. So we could use change of base, or we could use taking the log of both sides. Since I did change of base in this example, we'll go back to taking the log of both sides like we did previously. And I'll take log of both sides. So I'm going to do log of the left side and log of the right side. And when I do that, I'm going to take the exponent and write it as the coefficient. So that's going to give me minus 5 minus 2x times log of 9 is equal to log of 431. Now I can divide both sides by log of 9. Divide that out, and we get negative 5 minus 2x is equal to, it's probably a good enough time to approximate here, so log of 431 divided by log of 9, I end up with 2.761. So now we want to get x by itself. So now we just have a nice linear equation, so we're going to add 5 to both sides. I'm going to come all the way over here. We get negative 2x is equal to 7.761. Divide both sides by negative 2. And we're going to get x, I like to use approximates here because these are not exact, right, since I rounded. X is going to be approximately 3.881. 3.881, negative 3.881. And again, for these two, you could have either used change of base or taking the log of both sides. I like to just show both. And then generally what I suggest is stick to one because you can just get really good at one and that's really all you need. But just to show you both so you can decide for yourself. These have been examples of solving Ickier exponential equations. Thank you for stopping by.